Hi there, and welcome to video 2 of the Exponential and Logarithmic Functions video series. Today we're going to have a look at differentiating exponential functions. Okay, here's our main set of methods here. When differentiating exponential functions, we bring the differentiation of the top to the front, and in an interesting way we keep the top indice exactly the same as it was. And so to differentiate this first example, e to the 5x, we differentiate the top, which would be 5, and we take it down the front, and we keep the top the same. So that's fairly straightforward. The differentiation of the top is 5, it comes down the front, and we keep the e to the 5x the same. This one here, e to the x over 4, might be a little better for our brain if we turned it into e to the 1/4 x. That'll allow us to recognize that the differentiation of the top is 1/4, and then it's e to the, well, it was originally x over 4, wasn't it? So we'll keep it the same as the original there. And then we could, if we wanted to, turn that into e to the x over 4, but those last two versions are pretty identical. Okay, so keeping to the method, bringing the differentiation of the top down the front. Now the differentiation of our 2x plus 4 here is 2, so it goes down the front. And we have e to the 2x plus 4. We're keeping the top the same. So not too bad. Differentiate the top, stick it out the front, and keep the e to the power the same as it was in the original question. Let me look at some more examples here. When there's a number out the front already, we're still going through the same process. We bring the differentiation of the top out the front. Now, if there's already a number there, those two results can multiply with each other. So the differentiation of the top here would be 2. So it comes down and makes a 6 by multiplying by the 3. And remember, we keep the top the same. So we differentiated the top. It was a 2. It multiplies by that front number that was already there in the question, and becomes 6e to the 2x. Here, to help our brain, we might turn that one into 3e to the minus 2x. Then when we differentiate the top, we get minus 2. So that makes minus 6e to the minus 2x. Now, just to put it back a bit more like the original, we're going to rearrange that into minus 6 over e to the 2x. So often we rearrange it to help our differentiation skills by taking a bottom and making it a negative indice, but we kind of have an obligation to put it back into the original format that it was in the original question. Okay, this one looks much harder, but it's not too bad. Even if we get an expression for the differentiation of the top, that still comes down the front. So the differentiation of this top bit up here would be 10x minus 7. We'll put that in brackets because it's the 10x and the minus 7 that should be out the front here, of e to the power of 5x squared minus 7x plus 9, because we're keeping the top the same as what it was before. So we differentiate the top, even if it's ugly, it comes out the front of the e, and we keep the top the same. Okay, this one has an x and a term with an e to the power of 2x. They're two separate terms, and because of them both having x's involved there, we need the product rule to happen. So let us remind ourselves of the product rule. Okay, we've set ourselves up for a product rule here. Y dash equals v u dash plus u times v dash. So our u in this situation is our x, and our v is our e to the 2x. So over here we're going to put our values for these. U is our x. U dash, the differentiation of x, is 1. V is e to the 2x. Now our rule for taking the differentiation of e to the 2x is take our differentiation down the front and keep the indice the same. So there are all our parts here. So let's piece together our product rule here. V is e to the 2x. U dash is 1. Plus our u is x. And our v dash is 2e to the 2x. Just to tidy that up, a little bit. We'll have 1 times e to the 2x is just e to the 2x. And our 2 and our x, we might just rearrange that to have the 2 out the front, and then the x, and then the e to the 2x. So we notice that they've got e to the 2x in each of them. Some textbooks for their answer might have a factorized version of that, because we have something common there. Some might not, but still. If we have that in factorized version, we have e to the 2x out the front. That would be times 1 plus our 2x there. Just another arrangement of an equally accurate answer there. So that's what we have for that one involving the product rule. We needed to do product rule because we had an x in the first section and an x in the second section. And we just follow through with our normal product rule arrangements there. Okay, moving on. Okay, this one, because we've got x's on the top and the bottom here, we will need to remind ourselves of the quotient rule, because this is the quotient rule arrangement. Alright, we've got ourselves set up now for a quotient rule arrangement. So our u is the top of our differentiation function here, and our v is our bottom. So let's over here set out all our different expressions here. U is e to the 6x plus 1. I might try that again because that's not all that clear. Let me get my writing a bit clearer. E to the 6x plus 1. Now u dash will be the differentiation of that, which will be 6e to the 6x. V is x squared, and the differentiation of that is 2x. So if we're filling in our quotient rule here, we have y dash equaling the following. We have v, which was x squared, times u dash, which is 6e to the 6x, minus u, which was e to the 6x plus 1, and times, I'd better put that in brackets there, multiplied by v dash, which is our 2x. Let's not forget the bottom of this quotient rule, which was v squared, which would have x squared there. And we'll neaten things up a little bit here. This can become, well, when the x and the 6x sort of get slightly rearranged, we can write it a bit more traditionally here, e to the 6x minus, we'll expand this through these brackets here to make minus 2x e to the 6x minus 2x over x to the 4. And then some textbooks would then factorize, because we've got a common 6x, common e to the 6x and a common e to the 6x in that section. It's not achieving a lot, but still, if we take that out as common, e to the 6x outside of 6x squared minus 2x in the brackets minus 2x at the end, all over x to the 4. Pretty yucky expression, but we've certainly taken the differentiation of an expression with e's in there and x's in there following the quotient rule. Didn't really make for a nice, neat answer, but still, we can do our best. Okay, moving on. Okay, now this one is a function of a function rule, because we've got an expression in the brackets here, all to the power of 5. Now, we'll follow our instincts for our rules up here, but we might have to add a rule as well when we remember the function of a function rule for differentiating exponential functions. So we firstly treat the question as if the bracket was an x. Now, if that bracket was an x, we would take the 5 out the front, and we'd have the bracket e to the 3x plus 1 to the power of 4. That would be a normal differentiation if it was just that. But we also have to multiply by the differentiation of inside the brackets when we're doing a function of a function rule. So the differentiation inside the brackets here That will be our 3e to the 3x. So I guess for function of a function rule, we need to add a third step in our methods, and that is to multiply by the differentiation of inside the brackets. Very plain English there, but that's our third step. We multiply the whole thing by the differentiation of inside the brackets. So we could neaten this up just a little bit by bringing this 3x out the front. They're both the 5 and the 3e to the 3x are multiplying by this bracket, so we could have in the end 15 e to the 3x, and then our bracket e to the 3x plus 1 to the power of 4. So it's a function of a function rule, a bit like you've done previously, whereby we treat the bracket as an x and process that. Then we've got to add that third step here of multiplying the whole thing by the differentiation of inside the brackets. Okay. So there we've seen a variety of differentiating with respect to exponential functions. Not a whole lot different to normal differentiating. We sometimes have to use the product rule and the quotient rule and the function of a function rule. When we are differentiating an exponential, though, the differentiation of the top comes down the front and the top stays the same. Other than that change, we're really setting them out like most other differentiations that we've seen before. Thanks.